My name is Dominik Dvorak and I work at the AIT, the Austrian Institute of Technology. And basically we're dealing with modeling, simulation, validation of automotive systems, so in the automotive sector. And my presentation is about modeling and simulation of a thermal battery stack model for optimizing the energy consumption of an electric vehicle. So welcome everyone to my talk about integrated modeling approach of an electric vehicle HV battery for optimizing the energy consumption. I'm Dominik Dvorak and I'm working at the Austrian Institute of Technology. First I want to give you a short overview about this presentation. So if at any time the text size is too small, please raise your hands and tell me. So I want to start with a basic input about modeling and simulation and why we're doing that at the AIT. Then I will tell you a practical example, so define a real-life problem, then following with a solution approach to the defined problem, the implementation of this solution approach, and finally simulation and result discussion. And at the end, there's some time for question and answers. So why are we using modeling and simulation? Modeling and simulation are commonly used tools in the automotive sector. They allow to investigate physical systems in different application scenarios and under different environmental conditions. So they eliminate the need to perform protected real-life tests, and so a lot of time and money can be saved. So this is a lot what we're dealing with at the AIT in my entire vehicle simulation team. Currently, energy efficiency is one of the main topics in the automotive sector. The target is to improve the maximum range of electric vehicles, to make it more attractive to people, to make more people get electric vehicles. So one approach would be to improve battery technology, but we're focusing on we're coming from another way. We want to reduce the energy consumption of auxiliary components of the electric vehicle to improve the range of the electric vehicle. So therefore it is necessary to develop and simulate an electric vehicle, and this is why what my presentation is about. I've developed and simulated an electric vehicle traction battery with focus on thermal aspects and on the cooling circuit. The modeling is based on a practical example, so I based my modeling approach on a real-life vehicle, and the model should be finally used to analyze and optimize the energy consumption that is required for keeping the battery temperature within a specific range. So let's define the practical example, so the real-life problem. I chose one off-the-shelf electric vehicle and analyzed the battery stack, so I tried to find a lot of information about the battery stack. Unfortunately, most of the car producers don't give as much information as you would need for a simulation. But I figured out that the battery stack consists of 88 serially connected cells. And as you want to reach a certain battery cycle life, you should be aware that the cell temperature does not exceed a certain temperature level, and that's what you need the cooling system for. So in my model, I would have to consider a cooling circuit, a cooling strategy during a certain load cycle and under specific ambient conditions. Unfortunately, there's no general solution, so that I just put my problem into a tool and the solution pops out of it. So I had to determine the level of abstraction for my simulation model, and I had to choose a proper simulation tool and model. And this is where Wolfram comes into play. I chose to use Modelica as a modeling language. Modelica is a modern object-oriented modeling language for creating complex multiphysical systems, and you can create your model by using algebraic or differential equations. I used a Wolfram System Modeler, as we heard before from Jan Burgard, as a simulation tool and as a graphical user interface for Modelica. So my solution approach, as I said before, deals with developing a thermal model of the entire battery system, including a cooling system and a cooling strategy. So therefore I used our smart cooling library, which was developed from the AIT. It can be used for modeling and simulation of cooling circuits, especially for automotive applications. And it consists of conductive heat transfers in pipes, prescribed mass flow, pressure, volume flow, pump models, fan models, motor models, and so on. And let's go on. This is the basic concept. So as I said before, the battery stack I chose consists of 88 cells connected in series. But as I put the focus on the thermal modeling, I just implemented a very simplified electric model. I also considered the air cooling flow between and above the cells. And we see here an overview about the concept of the chosen vehicle battery. We see here we've got one module of 40 cells. Then we've got here 2 times 4 cells at the side of the stack. And here at the end, we've got another 40 cells. And the air cooling flows in this direction above the cells and between the cells. And that's why I wanted to model. So let's have a short look at the very simplified electric loss model. Just modeled that based on the equation I squared times the resistance. So far I considered only a constant internal resistance. And the interface to the thermal model from the electric model is a thermal standard Modelica connector. I used a thermal current profile, the FTP72 cycle, which is a real-life driving cycle, which is very dynamic. We see that here. So this is the current load for one cell, for each of the cells. We see here the implementation. I hope you can see that properly. Yeah, okay, that's okay. So I've got the table here, the current table, which defines the current load over time, which is this one here at the bottom. Then the square element times the resistance, and the replicator element distributes the electric losses to each of the cells. So this component is an array which is connected to each single cell. So let's come to the thermal model, which is the main part of this contribution. I've divided that into 2 categories. The first one is a cell model. So far I considered only cell models with discretization 1. So I've modeled the cells with only one heat capacity in the middle to consider the ability to hold thermal energy and thermal conductances to each of the 6 surfaces. So as we've seen before, we're dealing with prismatic cells, and we've got one heat capacity in the middle and thermal conductance elements to each of the 6 surfaces. Based on the cell models, I've instanced the 88 cells within the stack model to consider the spatial cell interconnection and the cooling circuit. And we can see here the basic system model. Here we've got the air inflow. You can set a certain ambient temperature in which the cooling system sucks the air through the entire battery system. We see here the 2 times 40 blocks and the 4 blocks. And the current state of the model, I've considered only a volume flow. In the next stage, I will consider a real fan with applying a torque to the to the fan. So let's have a closer look at the 40 cells block, the thermal modeling of the 40 cells block. This is what the subsystem looks like. We've got here the flow direction going up, and to be able to explain more clearly how the cells are interconnected, let's have a closer look at this part of the diagram. So we've got here a detailed view. Let's analyze the cell 11, it's called. We've got thermal connectors in both directions here, in X direction. And we see here that I've modeled conductive heat transfer between two cells. So here we've got the neighbor cell, and here we've got the neighbor cell on the other side. And we see that between the cells there's some air flowing, which is cooling down the cells. And as well, on the top of each cell, we've got the airflow that goes above the cells to cool the cells down. And to make the model more realistic, I've also considered thermal conductance between the cells in Y direction, where no flow, no airflow goes through the cells. So for simulating my model, and in order to analyze the energy consumption that is required for keeping the cell temperature within a specific range, I had to parameterize the model. But here is where the problem comes in. It's pretty hard to measure the thermal characteristics of the battery system, as we cannot access all the single cells, because we've got an electric vehicle at the AIT, but we cannot just open the battery container and get out the cells and measure the cells. So it's pretty hard to get the real battery parameters. We would need to buy the single cells to measure the thermal characteristics and the electric characteristics of the cells in our laboratories. So this is why for the first try of the simulation run, I only used literature values for thermal capacity, conductivity, and internal resistance. So I've defined the ambient temperature to be 20 degrees. So this is what this element is about. So where the airflow comes into the system. And I defined an internal resistance of 3 milliohms. So for the first simulation run, in order to validate whether the model behaves in a realistic way or not. Furthermore, I considered a certain current load profile. So we've seen before the FTP72 current profile, and for this simulation I've used a sequential FTP72 current profile. So it's constantly repeating this current profile. And I found some information that the cooling strategy of the chosen battery system is a simple on-off hysteresis control, which switches on and off the fan, the cooling fan. And I've parameterized here the hysteresis. This temperature sensor is an array. So here we measure all the cell temperatures. We figure out what is the maximum cell temperature within the entire stack, and we react with the hysteresis control to the hottest cell in the entire stack. Then we make, here we've got a simple element which defines which speed the fan blows the air through the whole system. So far I've got only preliminary results. As I said before, we weren't able yet to characterize the whole thermal and electric characteristics of each single cell to have the exact battery model. But I used some values from literature, and so I could validate, for example, the cooling strategy and the thermal response of the cells during operation. And we can see here, I hope this, okay, yeah, you can see that. I've colored here the cells I was observing, so the cell temperature during operations, during the sequential FTP72 cycles. So we've got here the cell which is directly cooled down by the airstream which comes from the ambient, and surely the air as it flows over and between the cells will heat up, and so the cells at the back of the stack, of the battery stack, will get warmer and warmer. And here we've got the temperature profiles over time from the colored cells. The hysteresis limits are parameterized to be 308 Kelvin and 298 Kelvin. And we see here the red cell is obviously the hottest cell in the stack model. And the controller tries to keep that cell between those both limits. And we see also that the cells at the air inlet, let's take here this blue cell, is cooler than the cell at the back. Let's take the orange cell. So we've got a temperature distribution within the entire stack, and we can analyze the cells separately. We can see here also the repeating sequence of the thermal response, the sequential FTP72 cycle. And with this model, finally, if the parameters have been figured out and if the model is extended further, can be used to determine is it really necessary to have a certain size of cooling fan within the whole system, or is it sufficient that we use a smaller kind of fan to optimize the energy consumption for keeping the cell temperature within a certain range? So let's come to the conclusion. So I've developed and implemented a thermal model of a off-the-shelf electric vehicle battery system, and I've included the cooling circuit and the cooling strategy. I've calibrated the thermal model with literature values, and I proved the applicability and the realistic behavior of the battery system. And I proved that by using a practical application example. So in future versions, we definitely have to make some vehicle measurements to characterize our models and to have the real parameters for this certain kind of vehicle. Probably if we need the temperature distribution from within the cells, we could also just replace the existing cell models by a discretized cell model. So we could use, for example, 3x3x3 cell discretization for each of the cells. And probably we should also consider the thermal influence of the battery container, so the heat transfer to the ambient. And yeah, finally integrate the whole battery system into an entire vehicle model. Thank you for your attention.